Hi guys, this lecture is going to be about a concept known as self-attention. And before I get started, I just want to say all the untitled images, which are most of the images in this video, are from week 5 of Duke's Intro to Machine Learning course on Coursera. If any of the things that I talk about are kind of confusing, I'd highly recommend checking out those videos. They explain it like pretty um, it's pretty easy to understand, even if you're not that familiar with some of the prerequisite concepts. So if you get sort of if you want another source after this, I'd recommend you check that out, and it's free. Like, you can watch the videos for free. And a lot of the ideas described in this lecture are from this paper called "Attention is All You Need," which is over the past few years, it's like one of the highly cited papers in uh, natural language processing and machine learning in general. So if you're interested in more information, I would check that out after. Okay, so introduction to self-attention. Self-attention is basically an idea that's it's used to transform embeddings, word embeddings, to also take into account contextual information in a sequence, right? So if what I just said didn't make sense, don't worry, because we're gonna define some of those prerequisite concepts already. But just know that the idea of self-attention is is really important to understanding another sort of fundamental idea that has popped up in machine learning research over the past several years, and that is transformer networks. And transformer networks are at the heart of like some of the biggest breakthroughs, like OpenAI's GPT-3, which is they use it for language modeling, like to generate sequences, whether that be like language or even pixels in a photograph. So, anyways, self-attention is a very key component of the transformer network, and so we're going to be discussing, and it's also used for other stuff as well. So we're going to be discussing that throughout this lecture. Okay, but first we're going to talk about word embeddings. Maybe you already know there are like many algorithms that have been discussed previously in previous years of the club that are used in creating word embeddings, right? An example of this is word2vec. And basically, word embeddings are some sort of vector representation of a word. The dimension of these embeddings can be arbitrary, but we somehow there's many ways to like do this exactly, and I'm not going to go into how we create these embeddings, but you essentially want to somehow train these embeddings to somehow capture the semantic meanings of words. And so the what I'm referring to can be seen in these images here, right? So for example, if you sort of project your embeddings into like a 3D space, you would sort of imagine that the relationship between the vector for king and then queen would be the same, right? So when I say vector, it's like all these embeddings are just vectors, right? And so if you imagine plotting these vectors, you could imagine like a similar relationship between king and queen and man and woman, because they differ in gender. And so the idea is like each of these dimensions in these embeddings somehow captures different aspects of meanings of these words. And it's somehow obviously this is just a three-dimensional example, and that's like pretty simplistic, and it's unlikely that our ideas of meaning will exactly match to one of those dimensions, but for the sake of intuition, we visualize it like the pictures that I've shown here. Here you can imagine like country and capital. So and here you can imagine verb tense in a similar way that I showed here. And this is another image, but if you think about like a 10-dimensional vector, so think of the embeddings being 10-dimensional, and each dimension correlates with some sort of aspect of meaning, like whether or not this word relates to sports or whether or not this word relates to politics, and so on. Then you can imagine that the vectors or embeddings for king and queen would be quite similar in all the meanings except for gender, right? Where this positive signifies like male, and then a negative signifies female. And as I said before, it's unlikely that there's going to be like 10 dimensions that exactly match to concepts that we humans have in our heads. But the overall idea is that these vectors somehow represent the meanings of each individual word. And as I said, there's many ways to create these vectors, and you can actually find like a lot of pre-trained vectors, um, pre-trained set of embeddings online. Um, so that would be like a separate lecture, but just know that we have these embeddings already. Another key concept, I mean, this is probably pretty obvious to you, but it may not. Just know that when we do the dot product, which is just like element-wise product, and then we sum all of the products um, of two vectors. The dot product is basically a measure of similarity, right? If you are familiar with the definition of dot product, a dot b is equal to the magnitude of a times the magnitude of b times the cosine of theta. So you can see that, okay, these two are always going to be positive, right? So then when is the dot product going to be maximized? It's going to be maximized, well, what's the maximum value of cosine of theta? Well, the maximum is 1, and that is when theta is 0. Since theta is the angle between the vectors a and b, the dot product is maximized when the vectors that we're dotting, a and b, are most similar to each other, right? When they're in the same direction and when the angle is 0. And so more similar vectors will have a higher dot product. This is just, hopefully that makes sense to you. Okay, so combining those two ideas, we can now explore what the self-attention mechanism is. So the goal of self-attention is to basically, let's say we have a sentence, and for each of the words in those sentences, in that sentence, we already have embeddings, like I described before, right? We have embeddings or vectors that represent the meanings of each of those words. But since this is a sequence, there's lots of information. Like let's say we're trying to perform sentiment analysis on this sentence, right? Well, you could say that the individual embeddings are all you need to perform sentiment analysis, but those individual embeddings only capture the information of those individual words. They don't at all represent the relationships between different words, right? Like the contextual information of the sentence itself. When you have embeddings, they only represent information for each individual word. They don't really capture anything about a sequence, right? Because the embeddings represent individual words. And so the goal of the self-attention mechanism is to somehow refine the embeddings that we have that correspond to individual words so that these embeddings also reflect contextual information of the sentence or the sequence that we have. So in our embedding, we'll also have information about words, other words in the sentence. Okay, so hopefully that made sense. If not, like that's basically the key. Make sure to understand what I just said. So how can we do this? The self-attention mechanism is actually fairly simple. What we do for each embedding, let's say we're trying to compute the new refined code for or embedding for vector ck, right? This is some embedding for some word. Basically, we take this vector and then compute the dot product for this vector and every single other vector in the sequence, in the sentence that we have. And we end up with these RK values. And this RKI value is computed as follows. This is basically just a softmax. Inside are the dot products. And so basically all of these RK values sum to 1. And what these represent are the relative similarities of CK to C1 compared to the similarities of CK to all the other vectors in the sentence. So hopefully that made sense. Basically, what we're doing is ck.ci is a measure, as I mentioned before, dot product is a measure of similarity. So when we do this dot product, we're essentially measuring, okay, how similar is ck to ci? And then when we create this rki value using the softmax function, what we're doing is uh, assigning, we're basically calculating a relative, how similar is ck to ci, um, how similar is ck to ci relative to all the other vectors in our sentence. And all these resulting values sum to 1. And basically, after we have these values, we use these as weights to compute a weighted sum for all the other vectors in our sequence, uh, for all the n vectors, including ck. Rk to k will be somewhere here. And basically, we compute a weighted sum, which is then our new representation for ck. So to get the broader picture of what this is doing, we're basically saying, by computing these rk values, we're basically saying, okay, how much should we incorporate c1 into our new version of ck, which is signified by this like symbol c tilde, right? So we're seeing, okay, how much should we let c1 uh, adjust our new representation? How much should we adjust c2 with our new representation, and so on? And so now we have a new ck that not only has the original embedding information stored, but it also has information combined that basically um, is from all the other vectors, right, in our sequence. And this somehow captures the context, like the meanings of the surrounding words in addition to our original word as well, right? So now we not only have the information from our embedding, but we also have more contextual information from the sequence itself. And this is just another, I just made this other slide to have this thing here. This is just a formalization of the weighted sum. But basically, the RK values are just scalars. And so, we just perform a weighted sum to calculate the new CK. Okay, so that was basically the self-attention mechanism. In literature, in the paper that introduced this, they had the terminology query, key, and values, and you'll probably see that in many places if you explore like self-attention or transformers on your own. So I just want to mention what those are. So the queries are the CK vector, right? So this is the vector that we're trying to adjust, right, when we get the new C tilde K. Okay, the keys are all the vectors in the sequence that we'll be like dotting CK with and CI with, right? This is like CI when I is 1, and so on. So we basically dot these two, and then the values are what we multiply the scalars with to get our weighted sum. So this is just like assigning names to what we have with all the vectors in the self-attention mechanism. And if you go and read the paper Attention is All You Need, or a lot of other related papers, you'll probably hear that terminology as well. So it's just important to know what that means. So there's some modifications that we can make to the self-attention network to actually improve performance. One is to add skip connections between the word embeddings and the final output vectors that we have. Oh, and just to note, when we do this CK thing, we do it for every single vector, right? So here it's just showing one updated vector, right? We just do this for one CK, but we repeat the same process for every single vector in our sequence. if that makes sense, right? So first we set k equals 1, and then k equals 2, and so on. And we repeat this for all n vectors in our sequence. So basically, skip connections are um, when we do these when we have the self-attention network, before we pass in the word embeddings to the attention network, we basically save the embeddings and then give them back, inject them into the later part of the network when the new output, when when the c tilde when the c tildes come out of this end of the network. Basically, we also add in our original word embeddings, right? So there's some sense that some of the information from the original word embeddings can be lost when we do the weighted sums and everything for each of the CKs. And so by adding in the word embeddings back, it's not obvious that this would like make a positive impact on your performance, but it does. So we do it. And we also normalize the values too. Okay, the second modification is somewhat more interesting. You may have noticed that here the resulting CK vectors are like positionally invariant, right? Like, I mean, the order in which we present the sequence is not at all reflected in the CK, right? You can imagine that if we completely reversed the sequence, so Cn was in the beginning and C1 was in the end, um, that wouldn't change the final output vector of CK. But we know that in sequences, like especially like in language, order really matters. And so we need some way to capture this information. And so one way to do this is using positional encodings. So previously the output sequences were order invariant, meaning that whatever output sequence we had, the order is not at all reflected in the final output vector. So what we do is we inject these in the same way that we injected those word embeddings. We also inject positional encodings, where the vector looks like this. So basically, WK is defined as following, uh, and so basically odd uh, for odd elements of our sequence, we do use the sine function, and for even we use the actually sorry for even we use a sine, and then for odd we use cosine. Um, and basically the value that we end up getting for when we do this whole vector is deterministic, and it's unique for each position. And so using this sort of sine and cosine formulation, we can basically capture the positional information as well, right? So if we were in position 3 or compared to like position 4, the positional encodings would be completely different. And so this acts as a sort of signal for our network to also make use of positional information, which we previously did not had in our original like setting. And so combining those two modifications, the positional embeddings and the word embeddings, um, we now have um, people have found that drastically increases improves performance, right? Um, so the final sort of like network that ends up getting created or that is used is called the attention based sequence encoder, and we also add this feed forward network at the end of like after this add and normalize layer. And what this basically does is it gives us some more room to like learn. These are just weights that we can train depending on our task. So it kind of helps in that regard. And basically, what we have now is a way to start off with some sentence, get the word embeddings for every word in that sentence. And as we pass all of these through this encoder, we end up with output sequences, C tilde 1, C tilde 2, and so on. And each vector here um, has contextual information and the positional information all built in, like it's all in there now, right? That's what this network did. And so that's the main sort of idea behind self-attention networks. It's the idea that we start off with word embeddings that don't at all capture any sort of positional information, contextual information, and we end up having like these sort of refined, richer vectors that are richer in information. Um, and interestingly, you can think of this as sort of a modular piece to that can be used in larger networks, right? You can imagine that you take this block here and just stack it on top of each other, where the input sequences from the output sequences from this sort of module would be then passed on and act as the input sequence for the next sort of encoder. And if you do this repeatedly, you can get like very, very rich representations of your sequence as a whole, where each vector has all the contextual information stored in. So one interesting application of these encoders is sentiment analysis. Basically, you just take whatever we had before, average the vectors at the end, and once you have that average vector, you basically do the dot product with another vector that is basically learned for this specific task, and then for any sort of sequence, you can just compute this logistic regression equation, and then get the positive sentiment. So you do like learn, several parameters. Here, E is a vector, and you can also learn the weights here. Another application is predicting next word. So this is also pretty similar to the sentiment analysis thing, but basically, you average the vectors again at the end, and then you have for every possible word that you can predict, you have your own like vector, and then for every word in your dictionary at the end, when you have this average vector v, you just do the softmax uh, of the dot product with each individual vector for every word in your possible predicted list. Right? In every um, you have these vectors for every word that you could possibly predict, and so then you have the softmax equation, and then that basically gives you the probability that for every word, like what is the probability that that is the next word, right? Um, so you can imagine like an RNN could do this as well. So what's the advantage of like using these self-attention mechanisms rather than like a conventional RNN? And so the main advantage that we have over RNNs is that, I mean, the one obvious thing is like, okay, we have all this contextual information stored in our new updated vector, right? But another huge advantage that we have is that these can be like these all the operations in this encoder are can be easily optimized for parallel computation, like with GPUs. But with RNNs, since your RNNs operate like sequentially, and so you can only like get the next activations once you do like the current active once you do the current operations. But with self-attention, there's no reason why you can't compute like C tilde n before C1 or at the same time, right? You don't like nothing here depends on previous steps, except from maybe like the feed forward network, but that's like a very small portion, and that's not even sequential. So, like, it's much easier to optimize and improve the speed using um, self-attention networks. And so that's it. Thank you for listening. If you have any questions, just let us know.